Welcome back. In the last lesson, we learned how atmospheric pressure affects flight. Now it's time to dig deeper. We'll explore altimetry errors, vertical navigation, and how pressure interacts with weather and instruments in real-world flying. Let's get started with why altimeter accuracy really matters. Let's talk about altimeter errors. Even if your altimeter is set correctly, various conditions like temperature or pressure changes can cause wrong readings. These errors affect safety, terrain clearance, and even legal separation from other aircraft. Every pilot must understand how and why these happen. One major cause of error is temperature deviation. Altimeters are calibrated to a standard lapse rate. But in very cold air, true altitude is actually lower than indicated. This can be dangerous when flying near mountains or on final approach in cold climates. To correct this, pilots apply cold temperature corrections. Some approach charts include guidance on how much to add. In extremely cold airports, regulations may even require it. Altitude over flat land might be fine, but near terrain, corrections are critical. Another common issue is pressure change in flight. Flying from high pressure to low pressure without adjusting your altimeter makes it overread. You're flying lower than the instrument says. That's where the memory phrase high to low, look out below comes in. And the opposite is low to high, plenty of sky. If you forget to reset when flying into higher pressure, your altimeter underreads. That's less dangerous, but it can affect vertical separation and ATC coordination. Always monitor pressure changes en route. Let's go deeper into pressure lapse rate. On average, pressure decreases by 1 HPA every 30 feet of climb. This is how your altimeter estimates altitude. But real conditions may vary, especially near pressure systems or temperature inversions. For this reason, we refer to the standard atmosphere when calculating performance. If actual pressure or temperature is different from standard, then actual altitude, true airspeed, and engine performance can all deviate. Pilots must adjust accordingly for safety and efficiency. Now let's cover flight levels. Above the transition altitude, we set the altimeter to standard pressure, 1013.25 HPA, and fly by predefined levels like FL 100 or FL 350. This ensures uniform separation between aircraft in different sectors of airspace. Remember, flight levels are not true altitudes. Their actual height above sea level varies with local pressure. That's why we use QNH below the transition layer to get accurate altitude readings and ensure terrain clearance. As you descend, ATC will tell you to reset your altimeter to QNH. This usually happens when you pass below the transition level. That way, your altitude reflects true height above sea level again, not just a flight level. Let's imagine a mistake: you descend below transition level but forget to set QNH. Your altimeter might show 4,000 feet, but you're actually lower, possibly in danger. This is why transition procedures must be followed with precision. Pressure also affects VNAV, vertical navigation. Modern aircraft use barometric data to follow descent paths. Wrong pressure settings lead to early or late descents, causing path deviations and separation issues. It's critical in RNAV or ILS approaches. Pilots should always monitor updated pressure reports. Use ATIS, METARs, and ATC advisories to verify QNH changes. Small pressure shifts make a big difference, especially during low-level or terrain-sensitive approaches. Now let's focus on pressure gradients. These are differences in pressure between 2 points. A steep gradient means faster-moving air and stronger winds. These gradients are visible on weather charts as closely spaced isobars. Pilots should anticipate turbulence in these areas, especially near fronts or mountain waves. Flight planning should account for wind strength and direction changes due to pressure gradients. It's also essential for calculating ground speed and fuel burn. At cruise altitude, lower pressure means engines behave differently. True airspeed rises while indicated airspeed drops. Monitoring your Mach number, fuel flow, and EPR becomes critical to maintain stable, efficient performance at high levels. Let's now discuss Pitot-static system issues. If your static port is blocked, you'll get inaccurate altimeter and vertical speed data. Icing or contamination are common causes. Regular inspections and heating systems prevent these dangerous failures. If the static port fails, some aircraft have an alternate static source inside the cockpit. This backup works, but can be less accurate due to cabin pressure effects. Still, it's better than losing all altitude information mid-flight. No matter how experienced you are, never trust the altimeter blindly. Cross-check with known field elevations, GPS readings, and ATC altitude confirmations. Pressure-based systems need constant attention to ensure safe and accurate navigation. Reading METARs gives you the local QNH. For example, if it says Q1010, set your altimeter to 1010 HPA. That ensures your instrument reads true airport elevation, essential for approaches and level-off altitudes. If the arrival airport uses inches of mercury, you might see a 2992 instead. That's 29.92 in Hg, the standard pressure. Be comfortable switching between HPA and in Hg depending on where you fly internationally. When changing QNH between airports, remember to update it before starting descent. If not, your descent profile may be off. You might end up too low or too high if your altimeter isn't updated to the new local pressure. Altitude reports to ATC also change depending on pressure setting. Below transition level, you report altitude using QNH. Above it, you report flight level using standard pressure. Mixing these up can confuse ATC and other aircraft nearby. Some regions have higher transition levels, like 18,000 feet in the US. Others may vary by airport. Always check the AIP or approach charts before your flight to avoid confusion. You may be flying at FL 100, but if the QNH is low, your true altitude is lower than usual. If there's terrain nearby or airspace restrictions, this can be risky. Check terrain clearance, not just what your altimeter shows. Cold air can further reduce your true altitude. You might think you're 1,000 feet above a mountain, but actually be only 500 feet above it. Charts often show temperature correction tables, use them when needed. To stay safe, always compare your altimeter with the known elevation on the airfield. If the numbers don't match, troubleshoot before takeoff. It could be a setting issue or a mechanical one. Let's say you set QNH, and your altimeter reads 250 feet. If the airport elevation is also 250 feet, you're good to go. If not, double-check your settings or report the discrepancy before departure. Before descent, cross-check the ATIS QNH with your approach chart minimums. If the pressure is falling rapidly, you may need to add margin for terrain or change your descent point to remain safe. Pressure isn't just a weather factor, it's part of everything: altitude, fuel planning, oxygen use, wind, turbulence, and separation. Understanding it means making smarter decisions throughout every phase of flight. Managing pressure is a core aviation skill. With practice, you'll adjust altimeters instinctively, interpret METARs quickly, and apply corrections before they become problems. It's one more step toward becoming a professional pilot. In the next episode, we'll explore density, how pressure, temperature, and humidity combine to affect real aircraft performance. It's one of the most practical lessons for day-to-day flying. Get ready to level up your knowledge in meteorology number 04, density. Let's do a quick recap using real examples. Flying from high pressure to low pressure without resetting your altimeter, you're flying lower than it shows. In cold air, your altimeter can overread 2. These small errors become big problems when you're close to terrain. Always adjust for real pressure and temperature. Picture a winter approach in mountainous terrain. The air is cold, and you haven't applied a temperature correction. Your altimeter shows you're safe, but you're actually closer to the ground than you think. Understanding this helps you avoid dangerous situations on final approach. Now visualize a steep pressure gradient. On a weather chart, you see tightly packed isobars. That means strong winds are present. As a pilot, expect turbulence and possible wind shear. Plan your descent or approach early and stay ahead of the situation. Let's read a meta together. That tells you, wind from 270 at 15 knots, visibility is good, and local pressure is 1005 HPA. You'd set that in your altimeter to match local conditions accurately. Pressure affects more than your instruments, it's part of aircraft design. Manufacturers test systems at different pressures to ensure safety and performance. From cabin pressurization to engine fuel delivery, everything is built to handle changes in atmospheric pressure. On passenger flights, pressurization keeps the cabin at a comfortable level, usually between 6,000 and 8,000 feet. That's why your ears pop. It's your body responding to pressure changes. Pilots monitor this closely to avoid discomfort or hypoxia. So whether you fly a Cessna or a jet, pressure affects you. Every takeoff, every descent, every weather decision is influenced by it. Once you understand how to manage pressure, you'll fly safer and more confidently. Understanding pressure sets the stage for what's next: density. When pressure, temperature, and humidity come together, they determine how thick the air is. And that thickness affects lift, thrust, climb, and more. We call it air density, and it changes everything. In our next lesson, we'll explore meteorology number 04, density. You'll learn how density altitude impacts takeoff distance, climb rate, and true aircraft performance. It's where science meets real flying. See you there.